Hi class, welcome to the next section, chapter 4.3. Today we're going to talk about the product rule and the quotient rule. So these are two rules that are super important for us in our study of Calculus 1 and for finding derivatives. We're going to mix these two rules with the two previous rules. You're going to see the product rule and the quotient rule all over the place. It's very important rules. So let's go ahead and get into it. So let's say that our function can be described as the product of two other functions. Okay, so let's call our function h, and let's say that h is equal to f times g. Okay, where f and g are two separate functions. So my function can be looked at as two functions times each other. So you can think of this as like, let's say x times e to the x, or let's say a polynomial times sine, or e to the x times sine, or tangent times cotangent, just any two functions being multiplied, right? X times square root of x. Pick your choice, right? So I can take my single function and I can describe it as two other functions being multiplied, right? A product of functions. So then if I want to find the derivative of this function, I know that it has a limit definition, which is the limit as h goes to 0 of the difference quotient. Here I know it's kind of confusing because we're calling our function h and we see h everywhere, but the h here and the h here is not the same, right? This is a function name, right? A function name, and this h is a variable h. We're not going to expand it in this form, so don't worry. We're just using the notation, right? You've seen this all over the place, so we know that all these h's are not the same h, right? Two of them are variables and two of them are function names. But it still stands that the derivative of this function is a limit, okay? So since my h function is a product of two functions, I can rewrite this as f times g minus my f times g, right? With the difference quotients. I have h of x plus h, which is me plugging in x plus h into f and x plus h into g, and subtracting regular h of x, which is f of x times g of x, all over this variable term of h, right? This distance that we have for our secant line as it comes together and creates the tangent line. So we're going to do a little bit of manipulation here. I'm not going to actually try to expand anything out because I can't. I don't know what h looks like. I don't know what this f looks like, what this g looks like. There's nothing to expand. So I'm going to do a common trick that we do in mathematics, especially at the higher levels, and that is I'm going to add something and subtract it again right away, but instead of adding it and then subtracting, I'm going to subtract it and then add it. So I haven't actually changed the value, right? So if I give you $1 and then take it away right away, I haven't actually given you anything. So you see this a lot when we do things like completing the square in a quadratic, right? I'm adding a new c value and then I'm subtracting it right away so that I can complete the square. Okay, so it's the same thing, same idea. I'm subtracting something and then I'm adding it right back. So I'm only doing it so that it makes the math work. Algebraically, I haven't changed the value at all, right? So what this allows me to do then is then I can factor out my g of x plus h on the first half because it has a common factor of g x plus h, g x plus h. So I factor that out. That leaves me with f of x plus h minus f of x. And on the right side, I'm going to factor out this f of x because that's what's common here. I have a f of x and an f of x. So what that leaves me is the difference quotient, the numerator of the difference quotient for g of x plus h minus g of x. All of this is over h, so I can this half, and I can separate them. Okay, so I separate my two limits. So I get half and half. Now what I can do is I can take this g of x plus h and I can pull it away so that I have just my difference quotient, my derivative of f, and I can pull out this f of x as a limit as well and leave it as a difference quotient of g, or derivative of g. So here I have my derivative of f, my limit as this function for h goes to 0, Here I pulled out my function for h going to 0, which doesn't affect this function at all. And then this represents the derivative of g. So if you notice here, as h goes to 0, this just turns into g of x. So what I end up with is f prime times g plus f times g prime. Okay, so the derivative of f, this just goes to g. So as h goes closer and closer and closer, my outputs just get closer and closer to g of x. So this is just g of x. This doesn't have an h in it at all, so that's just f. And this is the derivative of g. That is my product rule. So if I have a function that is the product of two other functions, then the derivative of that function, as long as f and g are both differentiable, is the derivative of the first function times just the second function plus the first function times the derivative of the second function. So I'm alternating which function I'm taking the derivative of while I keep the other as the regular function and I add them together. Okay, so differentiate, leave alone. Add to that, leave alone, differentiate. That's how I think about it. I differentiate the first one, I leave the second alone. I add to that the same thing, except I leave the first one alone and I differentiate the second one. So let's go ahead and do an example or a couple of examples of using this. So let's say I have a function that is x squared times e to the 2x, and I want to find the first derivative. So I have to use the product rule, which means I take the derivative of the first function, so x squared will turn into 2x. I leave the second function alone. I'll add to that me leaving the first function alone and taking the derivative of the second function, okay, which I know is natural log of e squared times e to the 2x, e squared x. So if I simplify this now, I know that this just turns into 2. This will be e to the 2x. This doesn't simplify at all. Okay, and notice that I have some common terms. So when we do these derivatives, we always want to simplify as much as possible. So I have a common e to the 2x I can pull out, and a common 2 and a common power of x as well. Okay, so I pull out my common factors and I get 2x e to the 2x times x plus 1. So always simplify your derivatives in this course. Here we're going to find the second derivative. Okay, so which is nice because now here I have the product rule. Okay, if I left it in this form, I'd have to do the product rule twice. I'd have to do the product rule here and add to that another product rule. I guess this isn't that much better because using the second form, I'm going to use the product rule considering this as one function and this as one function. But as I differentiate this first function, I notice that it is a function times a function. So I'll have to use the product rule again. So I'm kind of using the product rule inside of the product rule as I find the second derivative. Okay. So again, remember, I can find as many derivatives as I want. So we're going to start doing multiple derivative problems here as we go through this course. So if I want to find the second derivative, I'm going to take the first function. This 2x e to the 2x is what I'll consider as the first one. If I wanted, I could consider 2x as the first function and e to the 2x times x plus 1 as the second function, but that's probably a lot more work, honestly. So I'm going to consider this one as the first function, and I want you to notice something else as well. Since we are adding these two separate derivatives for our rules here, it actually doesn't matter which one I differentiate first, right? So for instance, if I wanted to differentiate g, the second function first, and leave the first one alone, and then on the second one, differentiate the first one and leave the second alone, that's fine. It doesn't really matter the order. So like if I were to switch these around. So as I go through these, I can kind of choose which problem I like the best, right? Because I'm adding them together, so it doesn't matter which order I do it, as long as I go, I switch the order of which one I differentiate. Okay, so we're going to do that here for the second example, and I'll show you what I mean. Okay, so x plus 1 is a lot easier to differentiate than 2x e to the 2x, so I'm going to actually just differentiate this one first, which means that I'll leave this one alone and I'll differentiate this. X plus 1, the derivative of that is just 1. And so I'm going to add to that then the derivative of this one that is a product of functions, since it's a little bit more work. And I'll leave the second one alone. So I'm still switching the order. I'm differentiating one, leave the other alone, add to that, leave one alone, differentiate the other, right? But it doesn't matter which order I start that off as long as I alternate which function I leave alone and which one I differentiate. So if we're going to differentiate this now, we're going to do it as the product rule again. So I'm going to add to that 2x. So staying with doing the second one instead and leaving the first one alone, keeping it consistent so I don't get confused as I go. I'll leave 2x alone and I'll differentiate e to the 2x. I know that from the first part, when I differentiate e to the 2x, I just got 2e to the 2x. Okay. So I'm going to add to that then me differentiating the first term, 2x, and I will leave e to the 2x alone. And I'm going to multiply that times me leaving the second term alone. So you kind of have to keep track of what you're doing as you go, right? So now what I'm going to do is I'm going to simplify. This will be a 4x. This is a 2e to the 2x. If I want, I can pull out this common e to the 2x, which is actually common everywhere. So I'm just going to simplify slowly, right? So this just turns into 2x e to the 2x. Here I'm going to distribute this and multiply it out, right? So I get my 4x e to the 2x times x, which is 4x squared e to the 2x. Then I'll take this first term times 1, so that's just 4x e to the 2x. And then do the same thing here, so I'm going to get 2x e to the 2x. And then this will just be 2e to the 2x. Okay. I'm going to look and see what I combine for like terms. So I have a 2x e to the 2x, 2x e to the 2x, and 4x e to the 2x. Those three are all common. So that gives me 8x e to the 2x. This doesn't have anything in common, and this doesn't have anything in common either. So I'll just simplify as much as possible. Put my x squared term in front. Now I will pull out my common e to the 2x I have everywhere. Okay. And I'm left with this polynomial on the inside. Okay. If I can factor this, I'll try to factor it. If I can't, then I won't. And this is not factorable. So this is as far as I can pull it out. Right. So I have my first derivative for this function. Using the product rule, I have my second derivative. Okay. So there's a lot of algebra, which I did say we have in this class. So make sure you go slowly. Look for your common factors. Simplify as much as possible. If you can factor from there, then you want to continue to factor. Okay. So I didn't show it, but I would try to factor this. Either use a quadratic formula since it is quadratic. If I don't have nice numbers, then you don't have to try to factor it, or use your synthetic division with the possible zeros. Okay. Here we have, we want to find the derivative if y is this times this. Now there's kind of two ways to go about this. We could multiply this all out and then take the derivative, so that's kind of a lot of work. It's not a whole lot of work, but it can be, especially if we have very large polynomials in each place, which we don't. I kept it pretty light here. But we're going to go ahead and use the product rule. Okay. So let's go ahead. I believe we're going to take the derivative of the first one. Since they're both quadratics, there's not really one that's easier than the other. So we'll go ahead and just stick with the formula instead of mixing it up like I did for b. So we'll just do 2x plus 3 for my first term. And we'll leave it as x squared minus 1 for the second. So since I differentiated the first one and left the second alone, on the next set of terms, I'll leave the first polynomial alone and I'll differentiate the second. So times 2x. From here, I do want to simplify, so I'm not going to always multiply everything out. Here, I can't really avoid it because there's nothing nice going on. This x squared plus 3x plus 1, that's not factorable. This one is factorable, but there's no common terms to pull out, so we're just going to go ahead and multiply everything out and combine my like terms, right? So I'm going to do my binomial distribution here. 2x times x squared, 2x times negative 1, 3 times x squared, 3 times negative 1. I'm going to add to that me multiplying it as 2x. So 2x cubed, 6x squared, and 2x. I'm just going to combine on my like terms. So I'm going to have a 4x cubed 9x squared from this 3 and this 6. My x's is 2 and negative 2, so those cancel, and I have a negative 3. I would try to factor this if I can, and it's not going to work. There's nothing here that factors out. Okay, so I would leave my answer in this form. Now, the other way, here I says that it would have been more work, but technically it's not really a lot more work than what we did already, because we did have to multiply out some polynomials either way. So let's just say that we multiply this out beforehand, right? So we got the x to the fourth. We're going to have negative x squared. We're going to have 3 x cubed minus 3x, and then x squared minus 1. We simplify this, adding like terms, we get x to the fourth plus 3x cubed minus 3x, because the two squared terms cancel, minus 1. So now when I take the derivatives, very straightforward. I'm going to get my 4x cubed, 9x squared, minus 3. Okay. Which is what we had last time. 4x cubed plus 9x squared minus 3. Okay. 4x cubed plus 9x squared minus 3. So for the next one, I think this is our last one for right now until we go into the quotient rule. The next rule we have. We want to find y prime if y is square root of x divided by 2 to the x power. Now, if you notice, it doesn't really look like it's one function times another. It more so looks like one function divided by another function. Okay, but remember the way that functions work. If I have something on the denominator, I can rewrite it as a negative exponent. So my goal, if I'm going to use the product rule right now, is I need to rewrite this so that it has, so that it looks like product of functions. Okay, so I can rewrite this as square root of x times 2 to the negative x power. So now I can use my rules. I can use my product rule and my rule for differentiating exponential functions and for power functions. I know square root of x does not look like a power function, but it is, right? We can rewrite this as a power function, as x to some power. So again, rewriting this, I can rewrite this as 1/2 to the x and x to the 1/2 power, which is pretty nice. So let's go ahead and differentiate this. This is what I'm going to differentiate. I've taken my function and I've written it in as easy a form as possible for me to start to use derivatives, right? Using the product rule. So I'm going to take the derivative of the first term, which is natural log of 1/2 times 1/2 to the x, right? So we take the natural log of the base and then multiply that times the function itself. So natural log 1/2 times 1/2 to the x. And then I leave the second function alone. So I'll multiply that times x to the 1/2. I will add to that me leaving the first function alone and differentiating the second. So this will turn into 1/2 x to the negative 1/2. Okay. So remember what I said. I prefer to leave it in these kinds of forms. I'm going to pull out all the common terms I can, obviously, and I'm going to factor it out. But I try not to rewrite it as square roots and 1 over square roots and things like that. And so if we're looking for things to simplify, both of these have a 1/2 to the x, and they both have x to a 1/2 power in some form. Okay, so I haven't talked about it so far in this class. In my pre-calc class, we simplify things like this all the time. So when I simplify things like this x to the 1/2, when I'm looking for the common value to pull out, I always pull out the one that's negative. So I'm going to pull out an x to the negative 1/2, and what that does is this will go away, but I'm basically subtracting when I do that. So I'll have a 1/2 minus a minus 1/2, which will make a whole. So this will bump up to a whole value of x, and I will have a 1/2 to the x power and an x to the negative 1/2 in front. What'll be left over inside of parentheses is natural log 1/2 times just an x plus 1/2. Okay, there we go. So I'm pulling out the negative because both of these technically have a negative in them. So pulling out this negative, it just turns to 1, right? And then this one will give me 1/2 minus a negative 1/2, which bumps it up to a whole, actually. So the inside looks very nice. I don't care what this outside looks like. The inside of the parentheses looks nice. If I wanted to take this further, I would keep this 1/2 to the power of x, and I would divide this whole thing by square root of x, which I don't really need to do. It's fine the way it is. This is a preferred answer. This is the way I'm going to present answers to you in this class, and this is the way that I would like to see them on your exams and things of that nature. Okay, so next we're going to talk about the quotient rule. So the quotient rule is actually how we would normally approach number D, the one we just finished. Normally, when we have a function divided by another function, we use the quotient rule. There are times when we may prefer to change the way that they look so that we can write them in a form where the product rule is easier to use. But it just takes some manipulation and some insight into the way the functions work so that you can get them and manipulate them into that form. So if you don't feel like that, or that's just not a strong point of yours, and you just want to take it how it comes, that's when the quotient rule comes into play. So here, if my function is two functions being divided by each other, obviously the bottom function not being 0, both of them being differentiable, then the rule is different. So I'm not going to go through the long-winded limit explanation of finding this. I'm just going to give you the formula. It's very, very similar to what we had for the product rule, but it's a little bit different. Okay, here there is a negative sign. So in the product rule, I was kind of saying it doesn't matter which one you choose to differentiate first, as long as you alternate which one you're differentiating and which one you're not when you add them together. Here for the quotient rule, it does matter. So for the quotient rule, the first function is the one you want to differentiate first, and the second function is the one you want to differentiate second. It does matter because there's a subtraction here. So when you're subtracting things, it's not the same as like when you're adding and you're just moving things around. So it does matter the order that you apply this rule. You're going to divide that by your bottom function being squared. Okay, so you're basically doing the same rule as the product rule, but you're subtracting instead of adding. And then your denominator function, you are going to square that function. You're going to multiply that function times itself. So let's do an example. So same as the previous function we just had, right? Square root of x over 2 to the x. So instead of manipulating this thing and turning it into something where we can use the product rule, we are going to go ahead and use the quotient rule. So when I said before the first function is the top function. Okay, for the product rule, the first function was the first one that we saw. So here, it's the top function that we differentiate first, multiply it times this bottom function. We're going to subtract from that the top function being left alone and the bottom function being differentiated. And then we're going to divide that entire thing by that bottom function times itself. Okay. So we're going to differentiate the top function, so that's going to turn into 1/2 x to the negative 1/2. We're going to multiply that times the bottom function being left alone, so times 2 to the x. We're going to subtract from that our first function being left alone, so minus square root of x, or x to the 1/2, which is going to be nice when I try to simplify stuff. And we're going to differentiate 2 to the x, so that's going to be natural log of 2 times 2 to the x. Okay. We're going to divide that by 2x, 2 to the x times 2 to the x, or 2 to the x squared. So we do not leave it in this form. We have to simplify. Okay, we always simplify. So we know this 2 to the x squared is going to turn into 2 to the 2x, because that's what happens when you have an exponential function raised to a power. You just multiply those powers. Okay. As far as what's going on here, I have a common 2 to the x. Actually, to be honest, if you notice, I have a common 2 to the x in the numerator in each term and one in the denominator. So I can just cancel all of those and just leave a single 2 to the x in the bottom, because I have two of them, right? So I'll do that, and then really I just have to pull out a common value of x. So just like before, I have x to the negative 1/2 that's the value that I'll pull out of both. Okay, so first things first is, so instead of canceling each of these 2x, which is what I should have done, I'm applying this product rule, or this exponent rule here of an exponential function to a power, right? A power to a power. So I can simplify that and write it as 4x. Okay. So from here, I pulled out my common terms, which are 2 to the x are common on the top, 4 to the x is on the bottom. Each of these have an x to the 1/2, so I pulled out that x to the negative 1/2. I'm left with 1/2 on the inside, and then here, as we saw before, that bumps up to an x, and I have my natural log of 2. So that's what's left over on the inside. So I am going to simplify this further, but look and see what we have compared to what we had last time. Okay, I have a 1 over 2 to the x, x to the negative 1/2, natural log 1/2 times x plus 1/2. So the answer so far looks different, but as we continue through this, we'll see it's really the same thing. Right here you see I have 2 over 4, 2 to the x over 4 to the x. That can simplify, okay, to 1/2 to the x. This x to the negative 1/2 stays the same. Here this 1/2 minus x to the natural log of 2. Well, what happens when I apply this negative to a natural log? I can rewrite it as a power and rewrite this as a plus. Okay, so now I've manipulated it so that my answer looks the same. Okay, come back here, 1/2 to the x, x to the negative 1/2, natural log 1/2 times x plus 1/2. So it's the same thing. The order might be a little bit different. X to natural log 1/2, 1/2, x to negative 1/2, 1/2 x. So if you leave your answer like this, I would accept it. Obviously, this is a fine answer as well. If you left your answer like this, I would accept it as well if you simplify this part. Okay, so if you want to have negative x to the natural log of 2, that's fine. You don't have to apply this negative to make it a positive. I don't really care about that. That's not something I worry about. However, this 2 to the x over 4 to the x, if you left that, I would mark you down because you have not simplified it all the way. This is very obviously able to be simplified. So if you simplified that and left everything else the same, that's fine. Okay, this answer is fine as well. Actually, this is the answer I was saying. So this is a fine answer and this is a fine answer. So these last two are the answers I would accept. If you wanted to rewrite this x to the negative 1/2 as 1 over square root of x, I'd be fine with that too. Or if you want to put this whole thing over square root of x, that's fine too. There's other ways to simplify this which are okay. The way I think about it is, don't leave me with calculations left to do. If I have to calculate stuff, you're not done. And I'm going to mark you down for making me have to calculate stuff in order to figure out what your answer is, whether it's correct or not. Okay, so don't leave me with work to do. Put it into a simplest form. There's multiple simplest forms at this point in mathematics, so whatever you're comfortable with is fine. I'm pretty good at math. I can figure out what you're trying to tell me. Just don't leave me, again, with math to do, right? This would not be okay either because you can pull out common factors. You can simplify more. I would not be okay with this as an answer. Right. So find the derivative of f of x equals x squared minus 6 minus x squared minus x minus 6 over x minus 3. So this is pretty straightforward, a lot easier than the previous. So here there's actually, if you're able to see it, a really easy way to approach this, but we're going to just go ahead and factor this anyways, or differentiate. So I'm going to differentiate the numerator. So that's going to be 2x minus 1. Leave the bottom function alone, so just x minus 3. Okay, I'm going to subtract from that my numerator, and then I'm going to differentiate my denominator, so that's just times 1. And on the denominator, I'm going to have x minus 3 squared. Right? I don't really want to multiply this out if I could avoid this. And so from here, I really just need to simplify everything. So I'm going to multiply this through. Okay, 2x minus 1 times x plus 3 will give me this term. and then my x squared minus x minus 6, but changing the sign because it's negative. Then I have x minus 3 squared. I haven't changed this. Combine my like terms, get x squared. I have this minus x and this plus x cancel, so I have negative x 6x left. And then I have 3 and 6 is 9, which I can combine. Okay, I can factor, I'm sorry, which gives me 1. So my derivative is 1. If you notice, all the way from the beginning, x squared minus 6 minus x squared minus x minus 6 is factorable. And it factors to x minus 3, x plus 2. So right away, I could simplify that and have just x minus 2, and the derivative of x minus 2 is just 1, because the negative 2 goes away and x goes to 1. So there was a faster way to do this, but I wanted to show you how that worked. Okay. So again, I'm probably saying that here. So notice that if I was cognizant of it and I factored first, it cancels, and then the derivative of this is just 1. Okay. So now let's find the second derivative. So I've been doing a lot of these. What I like to do in my classes, especially when I'm like actually doing Zoom stuff and not video lectures, is I like to present a problem and then tell my students to pause my video and to work the problem and then to check their work against mine. Okay, we haven't really had to do that so much so far because a lot of the stuff we've been doing is either review or very conceptual, I would say. So this is us now getting into more mechanical arithmetic styles of calculus. So at this point, now that we've done a few of these, go ahead and pause it and find the second derivative. So maybe you're going to have a lot of trouble getting to the second derivative. Let's go with just the first derivative. So go ahead and pause it and find the first derivative, and then we will check your work against mine. Okay, so go ahead and do that now. And we're back. So hopefully you went ahead and tried to do this on your own. So notice that we have just a regular polynomial on top and then a product rule on the bottom. So now we have the product rule mixed in with the quotient rule. And that's the way it works, is you never know what you're going to get. And a lot of times we got to mix all these functions up. So we're going to differentiate the numerator. So that will turn into 2x. We'll leave the denominator alone. So that'll be times x times e to the x. We're going to subtract from that the first function being left alone, so minus x squared plus 1. Very important that you leave this in a parentheses. If you don't put this in a parentheses, it's very common for students to forget that they'll end up needing to distribute this negative sign. So either you write negative x times negative 1 right away, which still isn't going to help because you have to multiply it times something else. So it's very important that you keep it in parentheses, which, as you see, is something that I do a lot. So here, before I'm writing this x squared plus 1, it looks like I'm going to be differentiating this term first. Okay, so I'm going to differentiate the denominator just to get it out the way. So this 1 comes from me differentiating the first term, x, multiply it times e to the x. I will add to that x, and then differentiate e to the x, which is just e to the x. And this x squared plus 1, I leave alone. Okay, so I differentiated the first term, x squared plus 1. I multiply that times the bottom term, left alone. I'm going to subtract from that my first term being left alone times my bottom function being differentiated. The denominator here is just x e to the x squared. So from here, if I wanted to, I could go ahead and just start the second derivative from here, right? But I'll have to do the product rule. I'll have to do the product rule with the product rule on the inside of the quotient rule where I'm also doing the product rule. So it's really, really messy to do that. It's way easier to simplify now, right? So, because if I differentiate the numerator, I got product rule with the product rule, I got all kinds of stuff. So I'm going to just simplify, okay? I'm going to distribute this out. I'm going to multiply this out. This is 2x squared e to the x, okay? I can distribute this. I'll keep it negative, and then I'll distribute the negative later. So here, 2x squared e to the x minus, so x squared e to the x minus e to the x. So I'm distributing this negative as well. Here I'll have minus x cubed e to the x minus x e to the x all over x squared e to the 2x. From here I'm going to look for common terms in the numerator before I try to pull out any e's or x's that I have. So for x squared terms, I have 2 of them here, and I'm subtracting 1, so these 2 actually will turn into just a single positive x squared e to the x. This e to the x doesn't combine with anything. This x cubed doesn't combine with anything. Neither does this x e to the x. Okay, so I'm going to put them in descending order. So x cubed, x squared, the x, and then the positive, and then I have my denominator. So now I'm going to pull out my common e to the x in the numerator, and I'm left with this polynomial, okay, which is nice. It's not factorable, which is a shame, but it's okay. You can try to factor if you want, and you'll notice that you can't, but I can cancel one of these e to the x's. So this one will cancel. It'll be left negative on the outside, but this will turn into x squared e to the x on the bottom. Okay. So now when I try to differentiate, it'll be a lot easier because my numerator is simple, my denominator is fairly simple. I should probably distribute this negative first before I go ahead and differentiate so I don't get caught up in my signs. It doesn't really matter, it's up to you. But let's go ahead and differentiate. So I'm going to differentiate my numerator first. So that's negative 3x squared, positive 2x minus 1. Okay. I'm going to leave the denominator alone. So again, I'm using parentheses because I have 2 things I'm going to multiply. So this is just x squared e to the x. I'm going to subtract from that, me leaving this alone, but it's nice in its factored form, right? Pulling out this negative, because I'll just end up adding something. So that's pretty cool. So I'll go plus this, okay? And then the denominator now I have to use the product rule on. So I'm going to differentiate x squared first, so that's going to be 2x. E to the x gets left alone. I'm going to add to that x squared being left alone times the derivative of e to the x, which is just e to the x. So that's nice. And then this denominator is going to get squared again. So I'm going to have x squared e to the x squared. Okay. And from here, obviously, same thing. I want to simplify as much as possible. I can do that by multiplying everything out and then combining like terms and simplifying like I did here. Or if I'm a little bit sharper than that, I can look for common terms to factor. Okay, like here, I have an e to the x in each term. If I pull that out, I also have an e to the x here, and I also have an e to the x here, which is e to the 2x. I can cancel with one of them. So it looks like I didn't do anything from one line to the next. So I multiplied out the denominator. Okay, so I got x to the 4th now and e to the 2x. So from here I canceled my e to the x's, right? So I could have pulled out an e to the x here, and I would have 2x plus x squared. It doesn't really matter. I was just trying to knock down these e to the x's. So this is what I have so far. Here I could pull out another x, which would be nice because that will knock this down to an x and this to an x cubed, which is what I do here. So each one of these gets reduced by a power. So now when I try to simplify this numerator, it'll be a lot easier to do. So now, instead of having to multiply this crazy thing across here and multiply this across this whole thing and looking for what's common, I just try to be a little bit smart about my choices and pulling out common factors for things that I'll cancel because they're in each term in the numerator and denominator. So from here, I do have to multiply this out because I don't think this is factorable. This might be factorable, but even if it is, this one is not. So unless this has a factor of x plus 2, it's not going to be super helpful. So here I'm going to multiply in this x, so everything bumped up by a power. Here I'm going to multiply first everything times 2 and then add add to that everything, same thing being bumped up by a power of x. Okay, so I have now everything times 2, and then plus x4, x cubed, x squared, and x divided by this. And then I'm just going to combine all my like terms. Okay, so I have 1x4th. For the x cubes, I have a -1, a +2, and a -3. So those actually cancel out. No, they don't cancel out. They almost cancel. So this turns into a -1. Sorry, this +1. I have a -3 and a -1, so that's -4, and a +2, so there's -2 of those. For the squares, I have a x squared. This 2x and this -2x will cancel out, so that's just one of those. And for my x's, I have 2, I have 3, and then minus that 1, right? So I have the 2. And then one constant of 2 here. Okay, so I come down to this. I try to factor this as well. It was also not factorable over the integers, so I can't reduce down any more than that. So that is my final answer.